Hi, welcome back. This will be a lecture on the uniformly distributed stress related to principles of design. So, in order to begin with this explanation, we need to first consider some important properties of materials, which is stress. So, if I have a rod kind of structure like this, and we take a look at one of its cross sections in the middle. I'm going to denote that as A. That's the cross section. And let's say I apply two forces, force F on top, force F on the bottom. One of the stresses that I can talk about within this scenario is known as the tensile stress. It's denoted as sigma. And sigma is the force over the area. Notice this is very and very related to pressure. It's sort of the same concept, but in this case we're calling it tensile stress. It's how much stress is being put within this little rod. Okay, so that is pure tension and it is uniform. Another scenario we could have is where we have the same rod looking scenario. So if I were to draw that rod, same cross section within the middle, we'll call it A. Only this time I apply two forces on the right side and the left side. What's going to happen now? Well, we can say that there's another kind of stress, the shear stress, denoted tau. And tau is going to be F over A as well. Sometimes this is written as V instead. So if I were to take these guys out, also it's common in order to use V as your force, call it that, and say that tau is V over A. It's a very similar property. And the way, of course, that this material is going to deform as a result of this property is it's going to go from a normal circular shape as this, and it's going to sort of deform as it is being stretched and pulled laterally. So it's going to kind of look like that in a sense. So that's the way you can kind of think about it. Okay. Now, when we're talking about stress, how does that relate to beams? So let's say I have just a normal beam along a coordinate system. And I'm going to call this the y-axis, z-axis, and we'll throw in the x-axis. And I'm going to draw really quick here, just a normal beam. Like so. And let's go ahead and let's apply a moment at the end of this beam. I'm going to call that m sub z for a moment. And another way we can denote and call this moment is by using this little double arrow thing. That just means that it's a moment being applied there. It's not a force, it's a moment. And so yeah, we have this beam that we've specified. What can we say is the bending stress of this beam? Well, we need to take into account the moment about the z-axis, right? Because that's where our moment is being applied to. It's being the z-axis is in the middle of this moment. It's going through this circle. And so we can say that the bending stress across the x-axis is going to be equal to the negative moment across the z-axis times y over the area moment of inertia for the z-axis. Okay? And so we're trying to find what is the bending stress along the x-axis, kind of like we had with our two previous similar examples with the rods, along the x-axis, and it's highly related to what's going on about the z-axis for this beam. Okay? And I want to make sure that I clarify that the area moment of inertia about z is going to be defined as the integral of y squared dA. That is the area moment of inertia. Okay? And so just to visualize this beam, if I were to draw the same beam underneath this scenario, like so, that is how it would look, right? Because we have a moment being applied at the opposite end. Okay? And so we have our neutral axis going through the middle of this beam. And so how does the bending stress look? Well, if we were to take a cross section of this beam at one point, any point, and take a look at the bending stress, the way that the bending stress would behave, we can draw sort of a line that goes past the middle. And we can see here that the arrows begin to switch sections, switch sides. So on the top here we have some compression, because we can see that the top is being sort of squished, while the bottom is in tension as it is being pulled apart. So that's why the arrows change directions. And that's how the bending stress is behaving for this scenario. So what's more? We talk about a little more things with some beams. I'm going to go ahead and clear this up here, like so. I'm going to do another example here using a beam with a coordinate system. Only this is a cantilevered beam, meaning that it is fixed at the wall. And so as I draw this, I want to make sure that it is fixed at that wall. And I can simply write that using these lines. So that's a fixed beam. Okay, and then we're going to put a distributed load on top of this beam. So we're going to say there's a uniformly distributed load on top of this beam, which is 50 pounds per inch. And then we're also going to put a force on the side of the end of this beam as 100 pounds. So just looking at this beam and knowing what we have from the previous example, where is the maximum tensile stress? Where's the maximum tension that's going to occur in this beam? Well, if we know that it's fixed to the wall, then we know that that all of this distributed load right here is going to take full effect at the wall, because then that's where it'll be able to be under the full influence of those forces. So, knowing that, we know that it's going to be a point on the wall, or on this where it's attached. And if we're thinking immediately about tension, well, if we're looking at the uniformly distributed load, then the maximum tension, the behavior of this beam is going to look somewhat like this, if looking at it from this side. And so the max tension is going to be at this point on top. So we can already say it's going to be somewhere up here on the top. And then if we're looking at the beam from the top, we know it's going to look something like this, in which the max tension is also going to be at a corner right here. So here's 100 pounds, and here is our distributed load. Knowing this, I can go over to my illustration and I can point out exactly where that max tensile stress is going to occur. I'll say max tensile stress right there. Okay. Now that's good, but where does the maximum compressive stress occur? Well, if we use the same diagrams from before, right here, we know that the maximum compression is going to be down here is compression, because it's being squished. Down here is compression, because it's also being squished by both the distributed load and the single force. And so I can say that because of that, down here is going to be the max compressive stress. Now, if we were to have bending in both the xy and xz planes, sigma x is a little more complicated than what we started out with. It's also going to be negative moment about the z times y over iz, but it's also now going to be another component to this because we're talking about the planes. We're going to add the moment about y times z over the area moment of inertia of y. So that's our formula when we're using the planes because we need an extra component in that case. So this is pretty much just an introductory covering of some of the principles, some of the tools that we'll need going forward within principles of design. This is really going to help us be able to get our bearings and understand some of the mechanics that are going on behind these materials. Thank you.